What is the mechanical advantage of the pulley system shown below acting on a load with mass M? So let me kind of re-sketch this a little bit here, just so I could be specific. I'm not going to spend a lot of time on each part though, but let's say, okay, here's like that first pulley, and then there's a second pulley kind of right next to it. Here, not drawn as well as we have in the original there. Here is a rope or something going over that pulley, and it connects to this third pulley that, okay, my drawing of it's not so great. Here, and let's see, it looks like it goes around outside here and then comes back, sort of attaches right there, and then hanging underneath that is the mass that we're trying to lift. I don't think we actually need to do anything with the fact that we've labeled that as a mass M, because really what we're interested in here is we have an input force, and then there is an output force here that is lifting this mass up. I mean, really that output force is equal to the weight. You could say it's equal to mg, but I don't think that's actually going to be useful. The way that I look at this, though, at a pulley system, that is a good pulley system will work in such a way that the tension force is a constant throughout all these ropes. That's what good pulleys will do. And as long as, like, you can say, like, well, how is that really done? If things are quasi-static and not moving too quickly, it turns out that will be true to a large extent. The one issue might be is that the pulleys themselves and the rope could add some weight to the system that might cause some slight variance in the tension as a result of that, some of that weight sort of adding a pull depending on where you are. So for that to hold true in reality, what we'd like to say is that this mass we're lifting is quite a bit more, a larger amount of mass than the pulley system and the rope itself. So we're kind of working under those assumptions. But based on that, that means that if I look at, like, I can look at some different systems, right? But definitely F out is applied to this mass right here through this connection, right? But if I kind of look at maybe the system of just this bottom pulley here, and if each of these three connections right here, these three ropes, if each of those has a force F in, right? I don't know if you can see, it's going to leave enough space. Okay, so there's three F ins there. In other words, if I draw a free body diagram for that pulley, it turns out it would be appropriate for that one to say that the F out is actually pointing down on it, because that represents the downward pull of the object that's being lifted. So that's really the kind of Newton's third law reaction force to the force that is drawn right here. But this pulley is lifted up by these three tension forces, right? And each of those three, those are the three F ins that I tried to label in the picture, but they turned out really messy. But that means, right, so like if I look at this from a force balance perspective, I think it's kind of obvious to just say, well, that means there's a F in plus F in plus F in equals F out. I suppose if you want to be really formal and you looked at it from a perspective of net force, actually I guess I don't really need summation notation if I just say net force, right? Sometimes we say sum of forces, but I'm just saying net force like that is equal to 0. Maybe that should be a vector equation. So if I really wanted to get formal, I could say, okay, but the y components involve these three forces up and one down. So it would be kind of like maybe 3 times F in minus F out is equal to 0, which really is equivalent to what this says, right? In other words, this is saying that 3 times F in is equal to F out. But that means that if I solve for the ratio F out over F in, that's just equal to the number 3. So that's the answer I'm going to report, is it's equal to 3. One could ask, like, was it exactly equal to 3? Well, in reality, I mean, we kind of made the assumption of equal tension everywhere. So in reality, it may not be exactly 3. But I'm going to say from a mathematical point of view, it is exactly 3. And look, the slide said 3.0, I guess, to make it look more scientific. I'm laughing a little bit about that. But anyways, the answer is 3.